Assalamualaikum and very good morning to Dr. Osama and all my friends. Today we are from Group 1. We'll present Chapter 6 titled Programming. I am Nurusna binti Mustafa, which will be followed by my group mates, namely Muhammad Alif Iqwan bin Zulkifli, Nurul Najwa binti Muhammad Ali, Muhammad Yusuf bin Sumardi, and Muhammad Izu Ikhwan bin Muhammad Yusuf. What is the problem solving? Problem solving is a process of finding solution to difficult or complex issues. So, problem solving, how do we figure out what to tell the computer to do? What computer to do? So, computer have to convert problem statement into algorithm using with stepwise refinement, and then convert algorithm into LC3 machine instruction. What is the debugging and how do we figure out why it did work? Debugging is the process of detecting and removing of existing and potential errors, also called as bugs, in a software code that can cause it to behave unexpectedly from computer. To prevent incorrect operation of a software or system, debugging is used to find and resolve bugs of defects. When various subsystems or modules are tightly coupled, debugging becomes harder as any change in one module may cause more bugs to appear in another. Sometimes it takes more time to debug a program than to code it. Debugging also can do examining register and memory, setting breakpoint, and so on. For the stepwise refinement, also known as systematic decomposition. So, for stepwise refinement, we have to decompose tasks into a few simpler subtasks. Decompose also each subtask into smaller subtasks, and this into even smaller subtasks, and add until you get to the machine instruction level. In order for electron to solve a problem for us, we need to go through several of transformation to get from the natural language in which the problem statement is initially expressed and to the level at which electron can be manipulated to do work for us. For the problem statement, because of the problem statement are written in English, they are sometimes ambiguous and or incomplete. So, how to start with the problem statement and end up with a working program? We will apply a process reference to a systematic decomposition or a stepwise refinement. So, decomposition will continue until each simpler task can be implemented as just a few instructions in the programming language we use. Programming constructs are basic building blocks that can be used to control computer programs. There are three main programming constructs, that is sequential, conditional, and iterative. These three constructs are extremely important. They can help you control the flow of your program, allowing you to specify how or when parts of your code are executed. Sequence is the first programming construct. In programming, statements are executed one after another. Sequence is the order in which the statements are executed. The sequence of a program is extremely important as carry out instruction in the wrong order leads to a program performing incorrectly. Sequential construct is used when we can decompose a given task into two smaller subtasks such that one of them has to be fully executed before we can execute the other. On subtask 1 is executed, we never go back to it. We continue with subtask 2. For conditional construct, also is used when the task consists of some subtasks such that only one of them needs to be executed, but not all, depending on some condition. If the test condition is true, we need to carry out one subtask. Otherwise, we carry out the other task, but we never carry out both tasks. Once one of these subtasks is executed, we never go back. Using the example from the first activity, when a message board appears asking the user if they want to end the program, if they click the yes button, then the response variable is set to a value of visual base yes. However, if the user clicks the no button, then the response variable is set to the value of visual base no. If the response variable has a value of visual base yes, the program will end. But if it has a value of visual base no, the form is refreshed instead. From the example, we can see that selection statements such as if-else allow us to be selective about the line of code to be executed. We can make sure that only some lines are executed depending upon the condition we set.
For iterative, do subtasks over and over as long as the test condition is true. This is for check each element of the file and count the characters that match. First, more char to check. If it's false, nothing happened. But if it's true, check next char and count if match, and repeat to more char to check. Problem solving skill. Learn to convert problem statement into step-by-step description of subtasks, like a puzzle or word problem from grammar school math. What is the starting state of the system? What is the desired ending state? How do we move from one state to another? Recognize English words that correlate to three basic constructs. Do A, then do B. It is sequential. If G, then do H. It is conditional. For each X, do Y. It is iterative. And do Z until W, it is iterative. LC3 control instruction. How do we use LC3 instruction to encode the three basic constructs? Sequential. Instruction naturally flow from one to the next, so no special instruction needed to go from one sequential subtask to the next. Conditional and iterative. Create code that convert condition into N, Z, or P. Example, condition is R0, same with R1. Code subtract R1 from R0 is equal. Z bit will be set. Then use BR instruction to transfer control to the proper subtask. Code for conditional. First, test condition. If it's true, do subtask 1, and if it false, do subtask 2 and go to next subtask. Instruction. Then we have generate condition. For question mark, is exact bit depend on condition being tested, and for C, it is PC offset to address C. Then we have subtask 1, and 111 is unconditional branch to next subtask, while D is PC offset to address D. Then we have subtask 2 in C and next subtask in D. Code for iteration. First, test condition. If it false, do next subtask. But if it's true, do subtask and repeat that process from test condition. Instruction. In A, generate condition. In B, for question mark, is exact bit depend on condition being tested, and for C, is PC offset to address C. In B, do subtask, and 111 is unconditional branch to retest condition, and A is PC offset to address A. And in C, next subtask.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Yusuf bin Sumardi, and I will continue this presentation about counting character. Before I start present about counting character, I want to discuss about meaning character first. Character is every letter, digit, and punctuation mark. There are also many characters that are invisible on screen, such as the space, tab, and large written character. If you see on left side in this slide, is show about main process of counting character, and a right side show of process in the main process. The meaning is big task into three sequential subtasks is called by initial refinement. And the big task of counting character is input a character, then scan a file, counting occurrences of that character. Finally, display on the monitor the number of occurrences of the character up to 9. And three of subtasks is first initialize, that is put initial value into all locations that will be needed to carry out this task. Input a character, set up a pointer to the first location of the file that will be scanned, get the first character from the file, and zero the register that hold the count. Second subtask is scan the file, location by location, incrementing the counter if the character match. And the last subtask is display the count on the monitor. But the next slide will be discuss the second subtask, that is B from three subtasks. Okay, this slide show about refining B, one of three subtasks in sequential subtasks. The meaning of this slide is refining B into interactive construct. The interactive construct can be seen in the diagram on the right. The diagram shows if the result is yes, then the process will continue with sequential subtasks. While if not, then the process will run B1, that is test character. If a match, increment counter get next character. And the last, after B1 process will back run B. This process will be repeated again if the result is not done. This slide also shows about refining B1. The meaning is B1 into sequential subtasks. The process B1 has another sub-process to perform the main process. The sub-process in B1 is B2 and B3. B2 in test character if match, increment counter, and B3 is get next character. After that, the result will be back into sequential subtasks to do B process. The next slide show about refining B2 and B3. B2 called by conditional and B3 is sequential use of LC2 register and instruction. If you see flowchart on the right side, that is process for B2 and B3. And the last step is LC3 instruction. Use command to separate into modules and to document your code. And we can see the diagram for more. Next slide discuss about debugging. You've written your program and it don't work. Now what? What do you do when you lost in a city? Drive around randomly and hope you find it. It's wrong. Return to a known point and look at a map. It's right. In debugging, the equivalence of looking at a map is tracing your program. The first, examine the sequence of instructions being executed. Second, keep track of results being produced. And the last, compare results from each instruction to the expected result. And next, debugging operation. Any debugging environment should provide main two. 1. Display value in memory and register. 2. Deposit value in memory and register. 3. Execute instruction sequence in a program. 4. Stop execution when desired. And next, different programming level offer different tools. High-level language, example C++, Java, and other. Usually have a source code debugging tools. For debugging at the machine instruction level, first simulator, second operating system monitor tools, and the last in circuit emulator ICE, plug-in hardware replacement that give instruction level control.
In slide 20, it shows how LC3 simulators begins. The execute instruction sequence button, and then the stop executions and set breakpoints button, and then the display or set registers and memories. And then slide 21, there are 3 types of errors. First, syntax errors. Syntax errors arise because the rules of the language are not followed. Then, logic errors arise because the program does perform the way it was intended to. And data errors arise because the program tries to perform an operation that is impossible to carry out. This is how to tracing the program, tracing the program, execute the program one piece at a time, and examining register and memory to see result at each step. Tracing means to simulate the execution of a program on paper, to step through the program line by line, showing how the variables change. Experienced programmers use paper tracing to debug programs. They also use software tracers called debuggers. Tracing is also a great way for beginners to learn a language, to understand in a concrete way that what each statement does. And then this is example 1, multiply. This program is supposed to multiply the two unsigned integers in R4 and R5. And it will come out with the result R2 14 and not 30. This is how to debugging the multiply program. The single stepping, breakpoint at branch, PC and register at the beginning of each instructions. Executing loop one time too many, branch at 3203 should be based on Z bit only, not Z and P. And in slide 25, it shows example 2, which is summing an array of numbers. This program is supposed to sum the numbers stored in 10 locations, beginning with 3100, leaving the result in R1. Next slides, I will be continue with my next members, Izo.
Okay, my name is Muhammad Izulikwan bin Muhammad Yusuf, and I will be continue to our presentation in chapter 6, and my slide is summing an array of numbers. This program is supposed to sum the numbers stored in 10 locations beginning with x3100, leaving the result in R1. So we can look at this chart here. R1 is equals to 0, R4 is equals to 10, R2 is equals to x3100, R1 is equals to R1 plus M in parenthesis R2. R2 is equals to R2 plus 1, and the last one is R4. R4 is equals to R4 minus 1. And how about R4 minus 0? If the R4 equals to 0, the answer is halt, or the meaning of halt is safe. And if R4 is not equals to 0, we refer back to the R1 and R2. Okay, now we look at this data. You can look at this data and you study by your own self. Okay, we move to the next slide. Okay, debugging the summing program. Running the data below yields R1 equals to x0024, but the sum should be x8135. We can look at this column here, or the start single stepping program. The PC with x3004 is the R1 is 0, the R2 is x3107, and the R4 is 10. But in R2, this should be x3100, not x3107. This is because loading content of M in parentheses x3100, not address. So we can change opcode of x3003 from 0010 LD to 110 LEA. Okay, we move to the next slide. For the example 3, looking for a 5. This program is supposed to set R0 equals to 1 if there's a 5 in 110 memory location starting at x3100, else it should set R0 to 0. We can look at this chart here. The R0 is equals to 1, R1 is equals to -5, R3 is equals to 10, R4 is equals to x3100, R2 is equals to M in parenthesis R4. How about R2 is equals to 5? If R2 is equals to 5, the answer is halt. And if R2 is not equals to 5, the answer we refer to the R4, R3, and R2. And this is same as R3 equals to 0. If the R3 is equals to 0, the data will be R0 equals to 0, or the meaning of that is halt. And if the R3 is not equals to 0, this is refer back to the R2 equals to 5. And you can look at this data or diagram here, and you can look at by your own self. Okay, we move to the next slide. The next slide is debugging the 5 program. Running the program with a 5 in location x3108 result in R0 equals 0, not R0 equals 1. This is because perhaps we didn't look at all the data. Put a breakpoint at x300D to see how many times we branch back. Okay, we see at these columns here. This column shows different data because didn't branch back even though R3 is more bigger than 0. This is because branch use condition code set by loading R2 with M in parentheses R4, not by decrementing R3. We can swap the x300B with the x300C, or remove the x300C and branch back the x307 To bench back the point, we can look at this column here, column address and contents, to you more understand about this debugging the 5 program. Okay, we move to the next slide. For the example 4, finding first one in a word. This program is supposed to return in R1 the bit position of the first one in a word. The address of the word is in location X3009 just past the end of the program. If there are no ones, R1 should be set to -1. So we look back at the chart here. R1 is equals to 15 and R2 is equals to data. And how about R2? In parenthesis 15 equals to 1. If this is true, the answer is halved, or the program is halved. But if this R2 into parenthesis 15 not equals to 1, its decrement R1 shift R2 left 1 bit. You can look at this chart again so you can understand more about the finding first one in a word. Okay, next is debugging the first one program. Program works most of the time, but if data is 0, it never seems to halt. Breakpoint at backwards branch X3007. If no ones, then batch to halt never occurs. Okay, this is called an infinite loop. Must change algorithm to either check for special case R2 equals to 0 or exit the loop if R1 is smaller than 0. We can look at these columns here. These columns 1, and this is columns 2. You can see how the difference getting in these columns here. Okay, we move to the next. Debugging listened length. Okay, this is the last slide of my presentation. Okay, first, trace program to see what's going on. Breakpoints or single stepping. Second, when tracing, make sure to notice what's really happening, not what think should happen. In summing program, it would be easy to notice that address X3107 was loaded instead of X3100. And the last one is test your program using a variety of input data. In example 3 and 4, the program works for many datasets. And be sure to test extreme cases, all ones, no ones, and so on. Okay, that's all from me and my group. We beg your pardon if there's any miscommunication or misunderstanding in our presentation. So I hope you enjoy the presentation from my group. Okay, that's all. Thank you.